Hello and welcome back to Introductory Astronomy. Today we're going to continue on the subject of stellar explosions, and last time we talked about type 1 and type 2 supernovae. Today I'd like to talk about type 1a and type 1b supernovae. A type 1a supernova is caused by the collapse of a white dwarf. It occurs when a white dwarf gains mass in a binary system and exceeds the Chandrasekhar limit, which is the 1.4 solar masses. Once it does that, it collapses. The white dwarf contains almost no hydrogen in its outer layers, which is why you're not going to see hydrogen lines in a type 1a spectrum. A type 1b supernova occurs when a massive star in a binary system loses its hydrogen-rich outer layers to its companion star. As a result, a type 1b spectrum will have no hydrogen lines. A type 2 supernova is caused by the collapse of a massive star. The massive star has developed an iron core and therefore has collapsed, and we will see hydrogen lines in its spectrum. Let's talk a little bit about the formation of the elements. There are 81 stable and 10 radioactive elements that exist on our planets. So a good question would be, where did they come from? This graph here on the right shows the relative abundances of different elements in the universe. So if you take a close look at this, you see a summary of the cosmic abundances of the elements and their isotopes expressed relative to the abundance of hydrogen. The horizontal axis shows each of the listed elements' atomic number, meaning the number of protons in the nucleus. Notice how many common terrestrial elements are found on peaks of the distribution, surrounded by elements that are tens or hundreds of times less abundant. Notice also the large peak around the element iron. The reasons for these peaks are discussed in the text. Here is a summary table of the abundance of matter. Of course, hydrogen, which is comprised of one proton, makes up 90% of the abundance in the universe. Helium is 9%, and the remaining 1% comprises the rest of the elements in the universe. Now, some of these elements are formed during normal stellar nuclear fusion. In this example right here, we see how 3 helium nuclei fuse together to form carbon-12 and some extra energy. Carbon itself can then go on and fuse either with itself and produce magnesium-24 or with alpha particles. An alpha particle is a helium-4 nucleus. So if it fuses with a helium-4 nucleus, it will form oxygen-16. The elements that can be formed through successive alpha particle fusion are more abundant than those created by other fusion reactions. Right here in frame A, we see that at high temperatures, heavy nuclei, such as silicon shown here, can be broken apart into helium nuclei by high-energy photons. In frame B, we see other nuclei can capture the helium nuclei, or alpha particles, another way of saying the same thing. So other nuclei can capture the helium nuclei thus produced, forming heavier elements by the so-called alpha process. This process can continue all the way to the formation of nickel-56, which belongs to the iron group. So the last nucleus in the alpha particle chain is nickel-56, which itself is unstable and quickly decays to cobalt-56 and then to iron-56. Iron-56 is the most stable nucleus, so it neither fuses nor decays. However, within the cores of the most massive stars, a process called neutron capture can create heavier elements all the way up to bismuth-209. Heavier elements than bismuth-209 are made during the first few seconds of a supernova explosion. Neutron capture is the formation of heavier nuclei by the absorption of neutrons. Now we know that adding neutrons to a nucleus does not change the element itself. It just creates a more massive isotope of the same element. Eventually, however, so many neutrons have been added to the nucleus that it becomes unstable and decays radioactively to form another stable element. Now, this is a slow process. Each successive capture of a neutron takes about a year. So most unstable nuclei have plenty of time to decay before the next neutron comes along. This slow neutron capture process is called the S process, and it accounts for the creation of stable nuclei up to and including bismuth-209. Any attempt to form elements heavier than bismuth by slow neutron capture fails because the new nuclei decay back to bismuth as fast as they form. During the first 15 minutes of a supernova blast, the number of free neutrons increases dramatically as heavy nuclei are broken apart by the violence of the explosion. The neutron capture rate is so great that even unstable nuclei capture many neutrons before they have time to decay. This rapid neutron capture process is called the R process, and it accounts for the creation of stable nuclei up to and including plutonium-242. Let's take a look at the supernova energy emission a little bit more closely. In frame A, we see the light curve of a type 1 supernova, showing not only the dramatic increase and slow decrease in luminosity, but also the characteristic change in the rate of decay about 2 months after the explosion, the time indicated by the arrow. This particular supernova occurred in the faraway galaxy IC 4182 in 1938. The crosses are the actual observations of the supernova's light. In frame B, we have theoretical calculations of the light emitted by the radioactive decay of nickel-56 and cobalt-56, which produces a light curve similar to those actually observed in real supernova explosions. So this shows that the theory of formation of new elements in supernova explosions produces a light curve that agrees quite well with the observational curves. Frame C is a composite image of the remains of the Kepler supernova. The Kepler supernova is the last supernova seen to explode in our own galaxy, and it happened in 1604. The bubble-shaped debris field resides about 3,000 parsecs away. It's about 4 parsecs across, and it's expanding at 2,000 kilometers per second. X-ray data are blue and green, infrared data are red, and the optical data are yellow. So as you can see, we have a cycle of stellar evolution. We have a cycle of star formation, then we have evolution, and it's kind of like a continuous circle that continuously replenishes the galaxy with new heavy elements and provides the driving force for the creation of new generations of stars. Clockwise from the top are an interstellar cloud, Barnard 68. Then we have a star-forming region in our galaxy, RCW 38, followed by a massive star ejecting a bubble, and about to explode. That's NGC 7635. And the last one is a supernova remnant and its heavy element debris, N49. So as you can see, we have a cyclic process. Stars form, evolve, and die. In dying, they send heavy elements into the interstellar medium. These elements then become parts of new stars, and so on and so forth. Here's a little summary of Chapter 21. A nova is a star that suddenly brightens and gradually fades. It is a white dwarf whose larger partner continually transfers material to it. Stars greater than 8 solar masses can have fusion in their cores going all the way up to iron, which is stable against further fusion. The star continues to collapse after the iron core is found, implodes, and then explodes as a supernova. Type 1a is a carbon detonation supernova of a white dwarf which gained mass from a binary companion and exceeded its 1.4 solar mass, which we call the Chandrasekhar limit. Type 1b supernova is an iron core collapse supernova that has lost its outer layers of hydrogen to a companion star. Type 2 is an iron core collapse supernova of a single massive star. All elements heavier than helium and up to iron, nickel 56 in the iron group, are formed in stellar cores during nuclear fusion. Elements heavier than nickel 56 and up to bismuth 209 are formed during neutron capture, the slow absorption of neutrons, the S process, in the cores of evolved stars. Heavier elements than bismuth 209 are created during supernova explosions by fast absorption of neutrons, the R process. Study Chapter 21.4 through 21.5 and be able to explain the origin of elements heavier than helium. Outline how the universe continually recycles matter through stars and the ISM. Until next time.